In this video, we're going to be looking at Newtonian mechanics and remind you of Newton's three famous laws. Now, it's important to know that these three laws will hold up in almost all situations of motion, provided that A, the speeds are not getting close to the speed of light. So if something is moving so fast that it's approaching the speed of light, Newtonian mechanics breaks down, and we actually need to use Einstein's special theory of relativity, which we will look at some later point. The other time when we cannot use Newtonian mechanics is if the objects that we're looking at are very, very small, so of the atomic level. And if they are that small, then we need to be looking at quantum physics. Therefore, if an object is larger than the atomic level and not moving at a speed of light, we can use what we're about to learn and what should be a review to most of you. So Newton's three laws depend on forces. What is a force? So the idea of a force, and I think that you've heard this term before, a force is a push or a pull. So imagine, some flat surface, and we've got a box on that surface, and we want to move that box. So to move that box, we need to apply some sort of force. And if we apply a force by pushing it or by pulling it, then we can create its motion. We can give it some acceleration. So Newton's first law is this. Newton's first law says if no force acts on a body, the body's velocity cannot change. And this has to do with the idea of inertia. An object at rest will stay at rest. An object in motion will remain in motion unless acted upon by an outside force. So if we have some box sitting on a table, it's going to remain stationary, which should come as no surprise, unless there's a force. Similarly, and equally important, if that box had some velocity, and if it was moving at some speed, it's going to maintain that constant velocity unless a force acts on it. Well, if we're talking about force, it would be important to give force a unit, and because Newton was so instrumental in investigating forces, the unit for force, the conventional unit, is called 1 Newton, and 1 Newton is the force that results in an acceleration of 1 meters per second acting on a 1 kilogram mass. So in other words, if we think about this box here, if this box or this cylinder here has a mass of 1 kilogram, and when we apply a force on it, it accelerates at 1 meter per second. We have defined that force to be 1 Newton. So it's a created unit. All units of measurement are created and standardized, and this unit is such, a Newton is such that it will accelerate, 1 Newton will accelerate 1 kilogram at 1 meter per second. So we have spent some time looking at vectors. Forces are a vector. So what that means that forces are a vector is that a force has both magnitude, so a size, and direction. So oftentimes there might be multiple forces acting on some object. So let's take our box again that's sitting on a table. Someone could be pulling on that box with some force F1, and maybe another person is pulling against it at some other force F2, and there's some other forces that are acting on this box. There's gravity that's pulling it down, so we'll call that Fg, and then there's a force that's from the ground that's pushing it back up, and we could call that is a special force, which we'll talk about later, but it's called the normal force. So in this case, there are multiple forces going on. But what we're concerned, what we'll be doing is thinking about adding up all of these forces to find a net force or a resultant force. These are synonymous terms. And as long as the net force equals 0, so that's what we're looking at. As long as the net force is equal to 0, Newton's first law says that the body's velocity cannot change. So this starts introducing this idea that the net force is related to the velocity, the change, or rather the change in velocity over time. So there's a relationship between force and dv dt. So if the net force is 0, then dv dt equals 0, therefore the velocity is not changing. But we know that dv dt is really a. So there's a relationship between force and acceleration. Okay, a couple of important ideas. When we are talking about Newton's laws, we need to be talking about an inertial frame. And an inertial frame is a frame of reference that does not move. So if we talk about a block sliding on the floor is not also moving. The floor we consider to be stationary. So the block is moving along a stationary surface. Let's consider the idea of a puck sliding on a frictionless table. So here we have, some table, and it's frictionless, and we've got our little hockey puck. You hockey players should like this. That's sliding along the table. Well, since it's sliding along a frictionless table, we haven't talked about friction yet, but that means that there are no forces that are affecting its velocity. The velocity will be constant. Because there are no forces acting on it. That makes sense. But what if that table was really, 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 really long and wide? And what if that really, really, really long and wide table instead extended from the North Pole all the way down to the equator? And we set that puck going down the table. What's going to happen there? Well, this is a case of a non-inertial frame. So let's consider that, there's someone that's on Earth watching what's going on. Someone is on Earth. Well, what's happening is that the Earth is spinning. So our Earth is rotating. And that should come as no surprise to you. The Earth is rotating. And we've got this table, that's coming down. And as the puck is going down the table, the Earth is rotating around it. So the table upon which the puck is sliding, the table is moving. So what would be the direction of the puck? Well, what we're going to see is that the puck is actually going to deflect off to the right. And that's because the table is moving away from it. So what someone on Earth is going to see is, if here's our table and here's our puck, they're going to see that the puck kind of appears to be moving in that direction. So since the puck is changing direction and velocity is a vector, that means that there must be some change in velocity, right? So if it's all of a sudden moving to the west, it suggests that there's some kind of force. It seems like there might be some sort of force pushing it in that direction, which is causing it to accelerate in that direction, which is giving it a velocity. But this is not the case, because there is no additional force acting on it. The reason why we see this change in position is because the frame is moving. It's a non-inertial frame. So when the frame is moving, Newtonian mechanics breaks down. Well, frame of reference is really important. If the person hadn't been on the Earth, but the person was actually in space, then what we would have seen, the land mass and the clouds and the water would all be rotating and rotating and rotating, and the table itself would be rotating and rotating. But along the table, what you would see is the puck just moving right down the table. Is that true? Well, yes and no. I mean, the table is going to be moving along, and as the puck moves down, if we think about sort of position of puck and table, at first, let's see if I can draw this a little bit better. When it starts at the far north, the puck is here, and there's the table. And then a little bit later, the puck is going to be, let's draw it with a different color. The puck will be here, and now the table is actually moving. And a little bit later, the puck has moved down, and the table has moved. So what the observer from the sky will see is the table sort of moving off to the right, but the puck going down at a constant line. Okay, so that's Newton's first law. Newton's second law. Newton's second law says that the net force on a body is equal to the product of the body's mass and its acceleration. And that makes sense. These are totally connected, because in his first law, what we were seeing is that the force was related to a change in velocity. And what we said is, that is acceleration. So the only additional piece here is he found out, Newton recognized the proportionality constant, which is m. So this is a hugely important equation for physics, which, net force is mass times acceleration. So this allows us now to connect what we were doing in one and two dimensional motion, and now we can apply forces to it and understand how the force relates to acceleration and therefore velocity and position. So since we need to know a lot about the net force so that we can understand the net acceleration on an object, one of the things that we're going to be doing a lot is drawing free body diagrams of all of the external forces acting on an object. So let's think about, you may have done these before, but let's review what a free body diagram is. So the first thing you should do is draw, a general diagram, sort of a picture of what's going on. So think about some object here, and John's pulling on it at 30 degrees north of east. So that's 30 degrees with a force of 5 newtons. And Karen's pushing, so she's pushing the same object at 50 degrees south of west. So here's west and 50 degrees south of west. So she's pushing, so that's going to be like going in this direction, with a force of 10 newtons. So the idea of a free body diagram is it takes our general picture and we write it in a nice sort of more concise manner. So we've got a force going here, 5 newtons, and another force coming here with 10 newtons. And this is 60, and this is 30 degrees. So if we want to find the net resulting force and the net resultant acceleration, well, let's break this down into components. So the force in the x direction would be 5 cosine 30 plus 10 cosine 60. So just breaking up the John's force and Karen's force into their x components. And the force in the y direction is going to equal Well, same thing, but now it's sine. 5 sine of 30 plus 10 sine of 60. So those are the forces in terms of their x and y position. So if we want to find the acceleration, let's find the acceleration in terms of x and y. So the acceleration in the x direction, well, if we know that force equals mass times acceleration, we just divide the force by mass. So the acceleration in the x direction is going to be 5 cos 30 plus 10 cos 60 all over the object's mass, which was 2 kilograms. And then we could do the same thing for y. You guys are smart students, so we don't need to go through that work. Okay, so let's think about the very important forces that we're going to be working with, just so that you see them once, and we'll see them a bunch later on. So first most important force, gravitational force. And gravitational force is the force due to gravity. And that equals mass times acceleration, where the acceleration is our gravitational constant. Okay, so that's the force due to gravity. And weight, when we talk about weight, our weight is the force due to gravity. What we're feeling as, my heaviness, or when we talk about like how much do you weigh, you weigh something because gravity is pulling you down. So your weight also is mass times gravity. What about your normal force? Well, the normal force is the force that's pushing back from the ground on you, preventing you from falling through the floor. So if we think about this block here, this block is on a table. There's a force of gravity pulling it down, but the block is not moving. Since the block is not moving, there must be some opposing force, the normal force, which is pushing back at an equal but opposite direction. So the normal force pushes against you to resist your force of gravity. And the normal force will be really important, well, for us to not fall through the floor and for your books not to fall through the desk, but also it's going to be really important when we look at friction. Okay, speaking of friction, friction is a force that acts in the opposite direction of something's motion, usually. So we'll look at some special cases later. But if we think about some block sliding along a table, often, if you were to push a block or a book or something along a table, eventually it's going to come to a stop. So if you were to give this some initial velocity, this will usually come to a stop at some point. So there must be some force that's causing it to come to a stop, that's changing its velocity. And that force is the force of friction, operating in the opposite direction of the motion. And the last really important force that we'll talk a lot about is tension. So tension is, we often talk about tension in a rope. So we've got some block here, and someone's pulling that block with a rope, and there's tension force that the hand feels pulling the hand toward the block, and then there's a tension that's pulling the block toward the hand. So there's two tension forces going on. It's the tension force the hand feels and the tension force the block feels on opposite sides. And what must be true is that these two forces on opposite ends must be equal in magnitude, but opposite in direction. They must be equal in magnitude because otherwise the rope would be accelerating at different speeds. The fact that the rope is moving as one object, implies that the rope must have equal forces throughout it. Okay, so Newton's last law, his third law, says that when two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. So if we think about this special case where there's a book leaning against a crate, the book is pushing on the crate, and the crate is pushing on the book. So the crate is pushing the force of the book because of object C is pushing to the left. So the crate is pushing the book to the left. Meanwhile, the force on the crate from the book is pushing it to the right. And these forces must always be equal but opposite. So to say this, the force of A acting on B must be equal to the opposite of the force of B acting on A. Okay, so why is there a skunk here? Good question. So the idea of Newton's third laws is pretty easy to wrap your head around, I think, in most scenarios. But let's think about this case where there's a huge truck and it's driving down the road, and running across the road is a skunk. And you've all seen those terrible moments where you're driving the car and you get that skunk smell and there's a skunk lying dead on the road. Well, so the truck is driving down the road and it's a huge truck and hits into the skunk. There's a collision, the truck keeps going, and the skunk is kind of left over here. So at that moment of collision, though, which is giving a greater force on the other? So the truck, the force of the truck on the skunk versus the force of the skunk on the truck. So oftentimes we think that the force of the truck on the skunk might be greater because the skunk is injured and lies there on the road and the truck keeps going, no issues. The truck is so big that, how could the skunk provide a force onto it? But that's exactly the thinking behind it. The force of the truck on the skunk equals negative the force of the skunk on truck. They're equal but opposite forces. The difference is that the skunk experiences a greater acceleration because its mass is less. So because the truck has such a great mass, because its mass is so huge, the truck's mass is so large, that it experiences very, very little acceleration due to that impact, whereas the skunk has such a small mass in relation to the truck that given that equal but opposite force, it has a greater acceleration, which is what causes the damage and the sadness. Okay, so those are Newton's three laws. In the next video, we'll look at a handful of sample problems that will help you think about traditional type problems that you'll be solving.